everybody. I'm Jerry. I'm an independent AI/ML researcher. Previously, I was a senior AI engineer at Digital Currency Group and a deep learning engineer at Intel. Today, I want to talk about something that every builder in this room cares about, and that's how to train your 7 billion parameter model on the same hardware that your decentralized nodes are running. A little bit background before we go on. At Digital Currency Group, I was part of developing and designing the decentralized AI systems. I have experience fine-tuning open source large language models like Llama, Qwen, Microsoft Phi across GPU-backed infrastructure. And at Intel, I was part of the TensorFlow core optimizations team, where some of the code that I shipped improved convolutional operations by 400% on CPUs using Intel's 1DNN core library. My research focus is resource-efficient fine-tuning. And so this isn't just research for me. I've been building and deploying AI systems for a while. And that's the lens that I want to share this with you. OK, so here's the problem. So a 7 billion parameter model right now would require around 100 to 120 GB of VRAM just to train. That's a cluster of H100 GPUs. It would cost around $50,000 to buy, or $500 for a single cloud run on GCP. But our edge nodes, consumer GPUs like 4090s, 3090s, they have around 80 to 24 GB of VRAM. So we see there's like a huge gap here. And this gap matters more in 2026 than ever, because models are getting bigger with MOE architectures. Public data is running out, and it's estimated to be completely gone by 2032. And soon, privacy will be non-negotiable, which means that on-device training would be not just preferred, but compulsory. Why does decentralized AI need this? So in a decentralized network, not everybody, first is heterogeneous hardware. So on a decentralized network, not everybody would be running the same hardware. Everybody would be running completely different. Like some person would be running like a 4090, someone laptop GPUs. So you need a uniform stack for all of this. Second is, like I said before, privacy may not be preferred. It may be compulsory. So data needs to stay on device. And thirdly, decentralized AI gives something that central AI doesn't, which is verifiable contributions. This means on-chain voting and incentive mechanisms which could enforce quality. So how do we close the gap between the 100 GB of requirements to 8 to 24 GB of reality? OK, so here's the full landscape from the most expensive to least expensive. So full fine-tuning. In this method, around all the parameters of the model are updated. So that could take 100 plus GB, as I previously talked about. And the next less expensive way is adapter layers, which is actually a much better option. Here, what happens is trainable modules are placed between frozen layers. And because of that, that reduces the model size from 100 to 60 GB because you're freezing the model. And after that is the real breakthrough called LoRa, which stands for low-rank adaptation. Again, here, the model is frozen. But what happens is, along with the attention layers, a few amount of tiny matrices are trained along with that. And this completely reduces the VRAM to 20 to 30 GB. And after that is QLoRa, which is basically LoRa plus quantized. So I have to tell you, LoRa stands for low-rank adaptation. QLoRa stands for quantized low-rank adaptation. So what happens here is the model would be, all the operations would be in 32-bit. Here what happens is it's reduced to 4 bits, called NF4. And this makes sure that the memory requirements come down to 6 to 10 GB. So with this, along with a couple of stability techniques like gradient checkpointing, early stopping, gradient clipping, this could definitely make it run on our edge devices. And if you add it with this technique called flash attention 2, basically what that happens is it recomputes attention and kernel fusion to run on the fast SRAM, and it's much closer to the CPU. So what that gives you is it gives you a longer context length. So LoRa has been actually there for a while now. I think it came in 2021 or 2022. But nowadays, there have been more advancements since then. And first is DORA, which stands for Weight Decomposed Low Rank Adaptation. So here what happens is the weight updates are split into magnitude and directions. They're updated and then projected back. Second is GALOR, which stands for Gradient Low Rank Projections. In this method, it's actually completely different because it doesn't touch the weights at all. It takes the gradients, projects them to a low rank space, updates them, and projects them back. Third is VERA, which stands for Vector-Based Random Matrix Adaptation. So basically, here what happens is a lot of the frozen matrices are similar. So instead of storing these matrices, what happens is it stores only tiny scalar vectors, which contains only the scaling factor. So that reduces the memory a lot. And this is very popular in distributed environments. And lastly is mobile fine-tuning, which I also came across only a few days back, in which models can be fine-tuned on our phones, which is like ultra edge, which is even more than edge. And they use C++ backpropagation for this. Okay, so what is that you need to use? Which framework that you need to use? I would suggest if you have a data center of A100s or H100s, you should definitely go ahead with LoRa or full fine-tuning. But anything after that, from RTX 4090 or 3090, 3080, which has less than 48 gigs of RAM, I think QLoRa should be your baseline. And that coupled with flash attention and the stabilizing techniques that I previously talked, that would definitely help to be able to train the 7 billion model on your edge nodes. Okay, so what's worked and what's really hard? So this is the exact stack that I used at DCG. This helped me to be the top performer across 7 decentralized AI tasks on the Flock network. And this, surprisingly, these techniques also helped me to reduce the accuracy gap while full fine-tuning. If we, like for example, when we go a few slides earlier, I was talking about how full fine-tuning is 100% quality and QLoRa comes to 90 to 95%. With those techniques, it is actually possible to make it just less than 1% gap between the two, if you know how to use it right. And here's what's hard and what most people don't talk about, is that in a decentralized network, as I previously mentioned, there's a hardware variance. So when in situations like that, it's extremely vital that you make your training stack that is good for the lowest tier and not just something that's uniformly working. It has to be uniformly working, but the lower tier needs to absolutely work. And secondly is quantization has a floor. So earlier in QLoRa, we are quantizing it from 32-bit to NF4, which is 4-bit. But if you go below that, there is a significant change, and you would start noticing it immediately. So quantization is not unlimited. It's not infinite. You can only quantize to a certain level. Thirdly is there's a coordination tax. So since we're doing it on blockchain, there's additional overhead that you need to budget for, like incentive mechanisms, staking, validators, and this would additionally occupy some space as well, and this is something that you need to look forward to. And last is data distribution gaps. So since everyone's data is private and everyone's training completely different, you don't know the exact distribution of their data. So because of that, the same model could converge faster on someone's data and converge slower on other people's data. So because of that, you need to be able to find ways to coordinate between that as well. And so if there's anything that I would like you to take away is that you don't need a data center to fine-tune a large language model, a 7 billion parameter large language model. And stack beats hardware. With the right training techniques, you can definitely be able to train those on the edge nodes. And decentralized AI needs this base because of heterogeneous nodes and privacy constraints. And I truly believe that the era of data center only LLM fine-tuning is over, and now we can do it on edge devices as well. And thank you. So I'm Jerry. You can find my details on screen, and you can contact me for implementation details. Thanks.